Well, I welcome everyone also, as Nick said, and it's a delight to be able to gather again after a 2-year hiatus. And we actually tried to have another climate change a discussion last year, and then the pandemic hit, and so we had to just stall this until we could get together again on Zoom. And this has been a great vehicle for us, not only to discuss and to see each other, but to be together as a community looking at climate issues, and those are the issues that we care so deeply about. Thank you all for being here. Thanks, Nick, for Trinity putting this together and for allowing us to have this format. And Jeff, I'll just turn it over to you. I think it's exciting that you have accepted our invitation to be our first presenter.
Okay, and I'm going to share my screen. And I want to say that if anything is unclear or you have a question, feel free to unmute yourself and jump in and ask, okay? And I don't know if I can see the chat while I'm doing this. I only have one screen. So the best thing is if I'm confusing you or I'm not being clear, please just unmute yourself and jump in. So what I'm going to talk about is a climate history of the Earth in the last 65 million years, okay? And, all right, let's change the slide. There it goes. So, susceptibility to change. And you will hear the naysayers say, well, the Earth's climate is always changing. Can everybody hear me okay? My sound is coming through, all right? Okay, good.
Yes, I can hear you fine.
Okay, good. They say the Earth's climate is always changing. So, you know, what can we do about it? Nothing we have anything to do with.
Plans are brought up to the Walton County Commissioners. Once again, I'll tell you exactly what the TDC is saying and what residents have.
Somebody needs to mute themselves. Okay, but actually, just because the Earth's climate is always changing, that doesn't mean that it changes capriciously or that we can't predict it. Climate is not as random as weather, and the Earth's climate is sensitive to small changes. And humans, I'm going to show you, are a significant enough force to affect climate change. I guess that should be effective in A there. So I'm going to talk about a bunch of different time scales. And we're going to start with a 100 million year time scale. That's going to be our first time scale. And then we're going to cycle down to a 100,000 year time scale. Okay, so we're going to look at these different orders of magnitude of time to look at climate variation. And 100,000 years ago, of course, the dinosaurs were running around. 100,000 years ago, we had the woolly mammoths running around. So we went from this hothouse world where we had dinosaurs to this icehouse world where we had woolly mammoths, right? And so that's what we're going to be talking about today. But first, we have to introduce this concept of changes of composition between these three spheres on the surface of the Earth. So on the Earth, we have the lithosphere, that's the Earth's crust, the solid Earth, the hydrosphere, that's the ocean, and the atmosphere, and that's the air. And the atmosphere is the least dense, it has the least mass, and it's the easiest to change. And it turns out that that's what affects our climate the most, is the composition of the atmosphere. We're going to talk about the transfer of carbon between these different reservoirs, the lithosphere and the atmosphere, and then from the atmosphere to the lithosphere, because it turns out that that's responsible for a lot of the variability that we see on the million-year time scale. On the 100,000-year time scale is a transfer between the ocean and the atmosphere. And when we deposit waste as a society, human society, we put our solid waste into the lithosphere, right? We put it in a landfill, we bury it. And you have to pay to get your garbage picked up at the curb and put in a landfill. We pay for that. And our liquid waste, we flush a commode, the waste goes out, we treat that waste either in a septic tank or in a municipal waste facility, and you have to pay for that. It's in your water bill. But when we dump our waste into the atmosphere, we don't pay for that. We dump that waste free of charge. So your tailpipe emissions from your car and the smokestacks from the power plants, all that carbon dioxide, which is a waste product, CO2 is a waste product, that is going into the atmosphere for free. Okay, so climate change is based on, it's caused by a failure of waste management. And what we have to do is start charging for the dumping of waste into the atmosphere. Okay, that's the solution to this problem. And it's a very simple waste management problem if people would just look at it that way. Okay, so I always ask this question of my classes. The Earth's lower atmosphere, that's the troposphere, is heated from the radiation of what celestial body? Okay, don't say anything, just pick an answer, A, B, or C. The Earth's atmosphere is heated by the sun, the moon, or radiation from the Earth. Which do you pick? The answer is the Earth. Okay, it's radiation from the Earth itself that heats the Earth's lower atmosphere. And you know that intuitively because when you're at sea level, it's warm. When you go up in the air, the mountains, it gets cooler. In the airplane, it gets cooler. So the Earth's atmosphere is warm, close to the surface of the Earth, and it gets colder as you go up. And that's because the Earth's atmosphere is heated from infrared radiation that comes from the surface of the Earth. Okay? Everybody with me? If you're not with me, say something. So, let's see if I can make this cursor move. Here, can you see my mouse? Little pointer moving around here? Okay, here's the sun. And the sun emits radiation in the visible wavelength band and some UV. And it doesn't really emit heat at all. It emits visible and UV radiation. And that visible and UV radiation comes from the sun, and that radiation passes right through the atmosphere because the atmosphere is pretty much transparent to visible and UV radiation. So that visible radiation comes through, the UV gets absorbed by the ozone layer to mostly that. So the visible radiation comes through and it hits the Earth. About half of that visible radiation is absorbed by the Earth and it's shifted to infrared radiation, and the other half is reflected. The reflected visible radiation is Earth light. So the moon, right, doesn't radiate visible radiation, it reflects it from the sun. The Earth also reflects sunlight. And about half of the sunlight that comes to the Earth is reflected. The other half is absorbed and re-radiated as infrared. That's IR, and that's a long wave radiation. Visible radiation is short wave. So that long wave radiation, the Earth's atmosphere is opaque or translucent to that long wave radiation. So that means that the Earth's atmosphere absorbs infrared. So the visible light comes through, half of it's reflected back out, this goes right back out, the other half is absorbed and shifted to infrared, and the Earth's atmosphere absorbs some of that, and that is what warms the Earth. So that infrared radiation coming from the surface of the Earth warms the atmosphere. So it's like your car. The Earth's atmosphere is like your windshield. The sunlight, when you park it at the mall, the sunlight comes through the atmosphere, the windshield. All of it comes right through. The windshield is transparent to visible radiation. And some of that's reflected because you can see inside the car. So that's all reflected light. You can see the seats, you can see inside the car. But some of that is absorbed by the seats and is shifted to infrared radiation. And that infrared radiation is trapped by the glass because the glass of your windshield is opaque to infrared radiation. And that's what we call the greenhouse effect. And the greenhouse effect is a good thing. Without it, the Earth would be a frozen bone. Okay, so we like the greenhouse effect. We just don't like changes to the greenhouse effect. Okay, that's what's going to mess us up, changes. So here we are. This is what the Cretaceous period that ended 65 million years ago. This is what ended the dinosaurs. This is what the Earth looked like then. And here you see North America, right? And look, Florida is underwater. And you could take a boat and you could sail up the Mississippi Valley. It was all underwater. And you go to the North Pole, the Arctic Ocean, and you could sail around there. So all this was underwater. And that's because this was a much warmer world and there was no ice on this world. So all the ice that's stored on land today was in the ocean. And because it was ocean, the ocean was a lot warmer, it expanded, and so it took up more room. And so on this Cretaceous Earth, there were no ice caps. There was no frozen water whatsoever, okay? So if there had been people then, they would have had to drink their gin and tonics without any ice cubes, because you couldn't get an ice cube on the whole Earth, okay? And so sea level was higher, it was much warmer than it is today, there was no frozen water. And also what was different about that world was that the carbon dioxide concentration, the CO2, was between 1,000 and 1,500 parts per million. That's a lot higher than it is today. Today, the CO2 concentration is 410 parts per million, okay? And in pre-industrial times, before the Industrial Revolution, the CO2 concentration was only 280 parts per million. That's back like in 1800, just 220 years ago. So in 220 years, the CO2 has gone up by 130 parts per million. It's almost gone up 50% in 220 years, right, since the Industrial Revolution. And then we're going to talk about the glacial times. You all heard about the glacial times. That's when the woolly mammoths were running around. Back then, the CO2 was only 180 parts per million. So what you can see here is over the time scales that we're going to be talking about tonight, the CO2 has changed by basically factor of 10, right? From 180 when it was a glacial time and then we had woolly mammoths to about 1,500 back in the Cretaceous when it was warm and the dinosaurs were running around. Okay, and I make my students memorize these numbers: 180 glacial, 280 pre-industrial, a mere 220 years ago. Today, it's 410 and going up rapidly. And back under Cretaceous, it was between 1,000 and 1,500 parts per million. Order of magnitude variation across this history of Earth. So, back in the Cretaceous, when the CO2 was 1,000 to 1,500 parts, and there were no ice cubes on the planet. You know, there were a lot of palm trees, it was warm, the dinosaurs running around. And here you see an artist's rendition of the Cretaceous period. And there's a pterodactyl flying around there. Okay, see those? There's your dinosaur right there, that's a T-Rex. And I just want to call your attention to this right here with the yellow arrow pointing at it. That is a volcano. So one of the reasons the CO2 was so high in the Cretaceous was there was a lot of volcanic activity. Volcanoes bring CO2 from the lithosphere. Okay, remember we were talking about the changes of carbon dioxide and carbon between the lithosphere and the atmosphere? Volcanism brings CO2 from the lithosphere to the atmosphere. And this happens on million-year timescales. This is a very long timescale process. Nothing like the life of a human or the life of our society. But on a million-year timescale, volcanism is a very important process for bringing CO2 from the lithosphere to the atmosphere. Okay? And so now we're going to talk about how we know these long-term climate records. So I'm going to show you in a minute a climate record that stretches from the Cretaceous. It's going to have a temperature record from the Cretaceous to the present, and it's going to have a record of carbon dioxide from the Cretaceous period, 65 million years ago, to the present. Well, you may ask yourself, how in the world could anybody know what the temperature has been for the last 65 million years? How can we know what the atmospheric composition has been like for the last 65 million years? And the answer to that is that the records are stored in deep sea sediments. Okay, so the mud on the bottom of the ocean, and here's a mud core you see right here, and that's collected by this special drilling ship that can drill deep into the sediments, hundreds of meters. And so the mud has been accumulating over millions of years, right? And so over millions of years, if there's something you can look at, some chemical marker in these sediments that somehow relates to the carbon dioxide concentration, then you can get that carbon dioxide concentration over this time interval. If there's something that relates to temperature in that sediment core, then you can get a temperature record. So sediments accumulate, so this might be the top of the core, here's the bottom of the core, and what you have here, depth is time in a sediment core. We call this a chronology, time sequence, okay? So these sediments have been accumulating over time at a constant rate. They build up and build up every year. Here's the time zero, this is now. Here's the past, going down, 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 older, 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 okay? So this is like you just read these going down like this. So that's how we get these chronologies, okay? And what we're going to talk about is these paleoproxies. Paleo means ancient, proxy means substitute, paleoproxies for temperature, paleoproxies for carbon dioxide concentration. Everybody okay? The paleoproxy for temperature comes from these little animals. This is a shelled organism. It's called a foraminifera. And we get the temperature record from the ratio of oxygen 18 to oxygen 16. This is stable isotopes. This is another whole class almost. You need like a bunch of lectures to get to there. But you use this stable isotope record to get to paleo temperature. And the paleo CO2 comes from the carbon 13, carbon 12 ratio, and these biomarkers, we call these things alkanones. And these are long chain ketones. They're produced by phytoplankton in the surface ocean, and their degree of unsaturation is a paleo temperature indicator, and their degree of 13C content is a paleo CO2 concentration indicator. So from the shells of these little organisms and from these organic biomarkers, we get temperature and we get CO2 concentration. That's how geochemists, paleoproxy people do this, okay? And so this is the record. So here you see on this graph, there's two graphs here, right? Here is today, time zero. And we go back in time to the left. So here's 10 million years ago, 20 million years ago, 30 million years ago, 40, 50, 60 million years ago. And here's the temperature of the deep sea here, right? And so you can see that, and this is a relative temperature scale. It's not absolute, but it goes 0 to 8 degrees. So we have an 8-degree centigrade temperature change here. And at the end of the Cretaceous, it was here, and it was going along, and then it reached a maximum in temperature at about 50 million years ago. And that was in the Eocene period. This is the Eocene thermal max. 50 million years ago, a maximum in temperature. And from then, the temperature has been declining and declining and declining. So for 50 million years, the temperature on the surface of the Earth, as recorded in the ocean, has decreased and decreased and decreased. And here you see it decreasing. The line goes from red to blue when we shift from a hothouse world to an icehouse world. So right around here, we get the developments of the first ice sheets in Antarctica. And that makes the temperature drop more. And then we get the development of the Arctic, the northern ice sheets here, and the temperature drops even further. Okay, so the temperature drops from about more than 10 or 12 degrees in the ocean over this period. Coincident with this temperature change, we have a temperature CO2 concentration decrease. So as I told you, in the Cretaceous, the CO2 concentration was between 1,000 and 1,500 parts. There's the best estimate of it. The line, the shaded area indicates the uncertainty about that line. And you can see the CO2 concentration reached a maximum 50 million years ago, coincident with the Eocene thermal maximum. So, and then the CO2 concentration decreased over this same time period and reached a minimum of about 180 parts per million in the Pleistocene, the glacial period. So CO2 is decreasing by an order of magnitude. Temperature is changing by 10 to 12 degrees centigrade. And so one thing this shows you is that CO2 and temperature are linked. When it's warm on the Earth, the carbon dioxide concentration is high. And when it's cold on the Earth, the CO2 concentration is low. CO2 concentration can vary by an order of magnitude from 1,200 parts to 180 parts per million. Temperature over the same period decreased by roughly 10 degrees Celsius. Okay? Any questions about this record? It's clear as mud, right? Haha. There's the mud. Clear as mud. That's a little paleo proxy humor. Okay, so why did the CO2 why did the CO2 reach this maximum right here? Why did the temperature reach this maximum in the Eocene? And it turns out that this temperature maximum and the CO2 maximum was driven by plate tectonics. And if you know about plate tectonics, you know that the Earth's crust is moving around. The Earth's crust is in motion all the time. And we're talking about million-year timescales here. And there's a process called seafloor subduction. And during seafloor subduction, an oceanic plate is thrust under the continental plate. And when that plate is subducted, that's what you call subduction, in a subduction zone or a trench, and the Pacific is rimmed with these trenches. When the oceanic plate is subducted, in the sediments on the surface of that plate, there's a lot of calcium carbonate. And that's those foram shells that we saw earlier, one of our paleoproxy indicators. These foram shells are on this continental plate. It gets under thrust and goes down deep in the earth, 500 kilometers. And as it does that, it heats up. And when you heat calcium carbonate, you evolve carbon dioxide that comes through the surface of the earth and exits at the volcano. So we have CO2 transferred from the lithosphere, from this plate, to the atmosphere by this process of seafloor subduction, and it comes out the volcanoes. And it turns out that 80 million years ago, during the Cretaceous period, India was located 64,000 kilometers south of the Asian continent. Now we know that today India is rammed into Asia. Asia and India are continuous. But 80 million years ago, India was down by Antarctica, okay? And it started moving because of plate tectonics. It was moving at a rate of 9 meters a century. That's 9 centimeters a year. That's like this far every year. A whole continent was moving, okay? And as it moved across the sea floor, that oceanic plate that was its leading edge was subducted, and that was subducted down under Asia, and that transferred carbon dioxide, which was on the sediments, from the lithosphere to the atmosphere. And then about 44 to 52 million years ago, at that Eocene thermal maximum, India collides with Asia. And when that does that, you can't subduct continental material, and you form a mountain range that's tremendous on the surface of the Earth, the Himalayas, right? And so you transfer from seafloor subduction to mountain building. And that happened at the Eocene thermal maximum, and that change, when India hits Asia, that turns the Earth and starts to decrease the temperature, okay? And so here's an artist's rendition of this process. So here's Asia right here. And here's this leading edge of the oceanic plate. And that oceanic plate has got all these little 4M calcium carbonate shells on it, right? And so it's going along, and these things are getting subducted under Asia, and they get heated up, and CO2 comes out the volcanoes. And so you're transferring carbon from the lithosphere to the atmosphere, and it comes out as CO2, million-year time scale. So India is moving very rapidly, and here it is a little bit later. India is getting closer to Asia, okay? And here is a little bit later, and India and Asia collide. And when they do that, you shut off this volcanism. You stop the volcanism. You stop the evolution of CO2 from the subduction process. And you build up this big mountain range, and you change from subduction, which adds CO2, to this thing called weathering. And weathering is a process where rocks dissolve by reacting with CO2 in the atmosphere, and this weathering process draws down the CO2. So when you stop this process of seafloor subduction, adding CO2 to the atmosphere, and shift to weathering because you've built up this Himalayan mountains, because India has rammed into Asia, you start to draw down the CO2. So weathering draws down the CO2 on a million-year time scale, okay? So here's India now, it's rammed into Tibet. It makes this Tibetan plateau, the Himalayas. This is an enormous feature. There's all this nice, fresh rock that's exposed to this high carbon dioxide atmosphere. And that rock reacts with the CO2 in the atmosphere, okay? You form CO2 plus water. That forms carbonic acid. The carbonic acid attacks the silica, and it comes down the streams, and it forms calcium carbonate again when it gets to the ocean. So this weathering process, and this is a complicated story, but the weathering process now is taking CO2 from the atmosphere and transferring it back to the lithosphere, okay? So this forms calcium carbonate back on the sea floor. All this carbon as CO2 is coming as dissolved carbonate ion is coming down these rivers. It gets to the ocean and it forms more calcium carbonate. And so here we are, India rams into Asia right here 50 million years ago. And at that point, the CO2 starts to draw down and the temperature starts to fall, okay? So the weathering process is now drawing down the CO2, and it draws down the CO2, the temperature decreases, and then you start to form the ice sheets. And when you form the ice sheets, you increase the Earth's reflectivity. And so now the Earth is reflecting more of that sunlight and absorbing less of it. So the Earth starts to cool off, okay? Because ice cover reflects sunlight. So once you start to form the ice sheets in Antarctica, more sunlight is reflected, less is absorbed, and so the Earth cools off even faster. And then you form the Arctic ice sheets, and the Earth cools off even more. So it just gets colder and colder. It's what we call a positive feedback. The weathering is drawing down CO2. It gets colder. The ice sheets form. The reflectivity increases, and the temperature gets colder and colder. Okay? So that's where we are. We're forming these ice sheets. And these ice sheets start to form, the Arctic forms 5 million years ago. Once we get ice sheets forming, then we have another place on the Earth where we can get a paleo proxy indicator, because these ice sheets are building up, building up, building up, building up every year, just like that sediment was. So now scientists can go and take what they call an ice core, and we can get a more detailed record of climate change since the ice sheets formed, okay? So here's these guys taking an ice core. It's more sophisticated than this, but this is a nice picture, okay? And so here is an ice core. It's just a core into the ice sheet, and the top is the surface, that's time now. And as you go down this ice core like this, it gets older and older and older. So we have a temporal record in the ice, okay? And from the water itself, we have oxygen in the water. We can get the temperature over time from the ice. And it turns out that the ice sheet is formed from snow. And if you remember, like Jack London, the huskies would bury down in the snow because they could breathe. The snowpack freely exchanges air with the atmosphere. And so this is all atmospheric air, and it has the same CO2 concentration as the atmosphere. But as that snowpack coalesces and forms into an ice sheet, that air is trapped in the ice. And so it's sealed in the ice. And so these ice sheets, as they accumulate, they're taking samples of the atmosphere for us, okay? So this is like a really great strip chart recorder. It's recording the temperature of the poles, because the O18 in the water, you can get the temperature record, and the ice sheet is accumulating air and it's moving up through time. And so you also have a set of samples in that ice where the air is sealed into the ice, and you have a temporal record of the atmospheric composition. So you can just go take these cores and slice them up in the lab and degas them, and you can get samples of the ancient atmosphere over time. And when we do that, we find that the Earth has bounced back and forth between a glacial state. This is the Pleistocene now, when the woolly mammoths were running around. We have a glacial Earth and an interglacial. At the beginning of the pre-industrial period, we're in an interglacial period here. The glacial periods are the Pleistocene, and during the Pleistocene, the ice ages. So this is like an ice age here. The ice came all the way down to New Jersey, a big old ice sheet. It came down into Europe as well. And when you store all of that ice on the continents, you lower sea level. So this is what sea level looked like at the height of the last glacial period, 18,000 years ago. And this broad continental shelf sea level was down 300 feet, 120 meters lower than it is today. And that's because all this water was stored in these big ice sheets, okay? So climate flipped back and forth between this glacial state and interglacial, and sea level would go up and down with these glacial advances. So when the glaciers advanced, sea level went down. You're transferring water from the ocean to the ice on land as you form bigger and bigger glaciers. And so you can see that temperature and sea level are also linked, okay? And that's the big issue for Florida, is that climate and sea level are linked as well as temperature, okay? So this is the record of the Pleistocene. And this we get from ice cores. And here is time 0 here. This is now. And this is the temperature. We get this from the ice composition, the oxygen ice composition. Here is the present interglacial. And you can see the temperature was much lower in the Pleistocene. Here's the 18,000 years ago when sea level was so low. Here's another interglacial period. Here's another glacial period. And so the climate's flipping between interglacial warm and glacial cold. Interglacial warm and glacial cold. And this pattern was driven by small variations in the Earth's orbit around the sun on a 100,000-year time scale. And what that would do was a little bit of sunlight change would be amplified by variations in CO2. So the temperature here, as the sun, as the orbit changed and the sun reached the Earth less and less, the temperature would go down, and that would cause the CO2 to go down and the ice sheet would increase. And so again, we see a linkage between temperature here. This is the CO2 concentration varying between 280. Okay, so here's time 0 over here. This is our CO2 concentration over here, going from 180 up to 280. And during these warm periods, the interglacial periods, the CO2 was 280, 280, 280, 280. During the glacial periods, it was down as low as 180. And so again, we see that temperature and CO2 are linked tightly and well correlated. Okay, so glacial and interglacial periods over the last, this is that 100,000 year time scale I was talking about, 0, 200,000 years, 400,000 years, 600,000 years. So the Earth, because of this weathering process, the CO2 was drawn down until the Earth was very sensitive to these small variations in orbital parameters that were then amplified by the CO2 concentration. Okay, so what's new? Biological force, on par with these geological processes, is now transferring buried carbon back from the lithosphere to the atmosphere on very rapid timescales. The coal, oil, and gas that we are burning, our fossil fuels, come from the lithosphere. And when burned, they're adding CO2 to the atmosphere. Okay, so this whole talk is about the transfer of carbon from the lithosphere to the atmosphere. So when India was moving rapidly across the seafloor from the end of the Cretaceous to 50 million years ago, India was releasing CO2 because of the subduction, the plate tectonics. CO2 was coming out the volcanoes and increased, made the Earth warm. Then India rammed into Asia. It formed the Himalayas, a giant fresh rock, and that caused weathering. The CO2 was drawn down over the next 50 million years until it got as low as 180 parts per million. And so the Earth was in this glacial state, punctuated by interglaciers. And then human beings came along and they took carbon back from the lithosphere and transferred it to the atmosphere. So it's lithosphere-atmosphere exchange. And human beings, our society, is an agent of geological change that moves CO2 from the lithosphere back to the atmosphere. So here are some more ice core records. This is just very recent records over 1,000-year interval. Notice our intervals are getting shorter and shorter. First, we talked about millions of years. Then we talked about 100,000 years. Now we're looking at 1,000 years. Here's today, the year 2000, 2020. This is going back to the year 1000. This is an ice core CO2 record. And in pre-industrial times, from the year 1000, the CO2 concentration was 280, 280, 280, 280, 280, 280, 280. 1800 comes around, the year 1800. The Industrial Revolution starts in Mariel, England. They start burning oil and coal. First coal, then oil. And the CO2 concentration increases exponentially, going up as high as 420 parts per million in today's world. That's an increase of 50%. That's 40% here, but this slide's a little old. Methane is another greenhouse gas, and it comes from rice paddies, it comes from mining fossil fuels, it comes from burning natural gas and not trapping it very well. You can see that methane was about 750 parts per billion, and it also went through this exponential increase with the advent of the Industrial Revolution and is increased by 240%. Okay, so human beings have changed the composition of the atmosphere since the pre-industrial era, and for the case of CO2, it's a lithosphere to atmosphere exchange. So this is that CO2 record going back to the 100,000-year interval. Here's CO2 for the last 400,000 years, and it went between 280, this dotted line, and 180, this dotted line. So here is an interglacial period. It went down to 180 during this height of this glacial period. Then it goes back up to 280 for this glacial period. It goes back down to 180. It goes back up to 280 on this 100,000-year periodicity linked to the orbital parameters, varying tightly between 280 parts per million and 180 parts per million. Okay? Then we go into the last glacial maximum, 18,000 years ago. Then we have the Holocene, an interglacial period. And then humans discover coal. And we start to mine coal, and the CO2 concentration increases exponentially. Here it is today in 2020. And by the year 2100, if things continue as they are, and they show no intention of stopping, by the year 2100, it's going to be almost 700 parts per million. And if you recall the Cretaceous concentrations, by the year 2100, we're going to be halfway back to the CO2 concentration that was in existence during the Cretaceous period 65 million years ago, when the temperature was a lot warmer and there was no ice on the surface of the Earth. Okay, we're going halfway back to the Cretaceous by the year 2100. What will happen by the year 2200? I don't know. And here's human population. All this fossil fuel has allowed us to have a lot more people on the Earth. Okay, and I mean, I think it's great. We can come into our house. We can control our temperature with the flip of a switch. I'm not saying that we shouldn't have electricity. We just need to find a better way to have electricity than digging something out of the ground and burning it. Okay, so here's the average temperature on the surface of the Earth since 1800. And you can see it's increasing and increasing and increasing. And the year 2020 tied the year 2019, well, whatever, 2016 for the warmest year on record. Temperatures are increasing, no doubt about it. And it's correlated with this increase in carbon dioxide. And this is the temperature over since the year 1000. Medieval warm period, little ice age, temperature now warmer than any time in the last 1,000 years. This is from 2000 to the year 0. Okay, so it's getting warmer. And as a consequence of that, the sea level is increasing. And that's what we need to really worry about here in Florida, because we are the canaries in the coal mine for sea level rise, okay? So here we are in 1700, sea level baseline at 0. We see that here's the Industrial Revolution, and within 50 years of the Industrial Revolution, the sea level starts to rise, okay? By the year 2100, it might be as high as 1 meter higher than it is today, okay? That is a source of concern. That's a big increase in sea level, right? And why is sea level increasing? Two things control sea level: polar and glacial ice volume. And we know that the glaciers are melting, so the water runs into the sea. And as the ocean temperature gets warmer, the water expands and takes up more room. So the sea level rises for these two reasons. This is a picture, y'all know, some have heard of Bruce Means, right? Everybody knows Bruce Means. Bruce Means took this picture in Alaska. He lived there when he was a kid. When he was 14 in 1955, here's this big glacier. He went back there when he was 66 years old in 2007. 52 years later, the glacier was gone. Okay, the glaciers are melting. That increases, no, it decreases the Earth's reflectivity. It makes the Earth warmer because the Earth is going to absorb more sun, right? So this is a positive feedback for warming. As the glaciers grew, they cooled the Earth down. Now the glaciers are melting and they're going to warm the Earth back up, okay? So this is another source of concern. And this is going to raise the level of the sea. Here's Louisiana, 1839, 1870, 1993, and now. Louisiana is losing a lot of land every year. There's a lot of reasons for this. One of them is sea level rise. This is and what is this going to affect? Here's the coast of Spain in 1960. Nice little village, right? Here's that same place in the year 2000. A lot of coastal development. If sea level rises 1 meter, what's going to happen to all this investment? This is our own coast. This is like Fort Lauderdale. Look how little the beach is. This is Daytona Beach. This is right here on our own coast, St. Vincent Island. See this tree right here? When this tree was alive, and it wasn't that long ago, the level of the sand was here. Now the level of the sand is down here. All these dead trees. They're dying because the shoreline is retreating because of sea level rise. This is the road to Tybee Island during a king tide. It's flooded. The mayor of Tybee Island has a part-time job on the mainland. He has to call in and say he can't get there a lot of the time. This is a nuclear power plant, Hutchinson Island, Florida. there's not a lot of freeboard on that nuclear power plant. Okay, if sea level rises a meter, what's going to happen? This is a nuclear power plant in California. Look at this, how this, have you ever been to Stump Hole over on, going out to the Cape San Blas, and the road goes way out into the Gulf because of all the rocks there to keep it from eroding? Well, they place rocks here to keep this power plant from eroding. Look at the cliffs here and here. The ocean would like to claim this area. This is in coastal Louisiana. All of our oil and gas infrastructure is just barely above sea level. And then finally, there's places like this, Bangladesh. Bangladesh is a large delta, just like Louisiana. It's a low-lying area. It's very crowded. The people here are Muslim. They're surrounded by India. The people there are Hindu. And we know that people of different religions, I mean, no offense between them, you know, they're not that happy with each other, right? So here's the border between India and Bangladesh. As Bangladesh floods, where are all those people going to go? And climate refugees, that's a problem now. All those people in Central America, well, the rainfall patterns have shifted because of climate change. They want to get out of there. And where are they going to come? They come to the border with America, and we build a wall. But this is happening all over the earth. All the Syrian refugees, all that Middle Eastern stuff is partly driven by climate change, desertification of the Middle East. Okay, and so that's my presentation, and I hope that you guys have some questions, and we can. I hope that was mildly effective, and that some of it came across. And if you have any questions, I'll be happy to try and answer them. Here's a question in the chat. Okay, anybody got a question? Yes, Rogers.
Hey, Jeff, on whether it's the mud samples or the ice samples, how is it determined? I mean, how do you know, going back in time, what represents the time itself? What constitutes 1,000,000 years or 1,000 years?
There are other chronometers for that. So there's radioactive nuclides like uranium series, and for the ice cores, you can actually count rings in the ice that come with thaw and freeze. And so it's like a tree ring record. You can see little layers in there, but there's all kinds of other tracers. People are so smart about figuring this stuff out. And there's all these chronometers, you know, like time clocks. And so they're radioactive nuclides and rings that you can count to get that. But they do an excellent job of that.
I'll ask a question.
Jeff, I have a question.
Today. How long would it take to get back to normal? Well, here's
Jeff,
yeah.
excuse me, would you ask him to repeat the question, please?
Okay, well, I'm reading this from the chat. It says, if we had the will to begin today, how long would it take to get back to normal? So the atmospheric residence time of carbon dioxide is 200 years. So if we stopped emitting carbon dioxide today and went totally solar, it would take, you know, it would be on a 100-year time scale to reduce that. But the good news is that the atmospheric lifetime of methane is only 10 years. And so if we could reduce methane emissions, we could see some impact on a decadal time scale. And because methane is a much more powerful greenhouse gas than carbon dioxide, like 35 times stronger, even though its concentration is lower, methane has 25% of the greenhouse forces on the surface, on the Earth's surface. So it's like 25% methane, 75% CO2. And that's an oversimplification. But anyway, we could reduce methane emissions and we would see a benefit on a decadal timescale. So that's what we really need to be focusing on. That's why it was so frustrating when the current administration released or reduced the rules on methane leaks from gas pipelines. We're doing all this fracking. We're going into methane in a big way. And we have to control those leaks on those pipelines, because a little bit of methane leakage goes a long way towards greenhouse gas effect. Okay, so Susan Robinson says, is in the past there were concerns about the thinning of the ozone layer. What is the current status of the ozone layer? Does that affect climate? Ozone mostly is an absorber of ultraviolet light. So until there was oxygen on the surface of the Earth, which only came about 600 million years ago, there was no life on the surface of the Earth. If you came to the Earth, a billion years ago, it would look like Mars. And you wouldn't see anything living there because the UV flux the UV light coming into the Earth was so intense. Nothing. If any kind of thing tried to crawl out under the surface of the Earth, it would get fried. But then oxygen built up in the atmosphere, and then that formed the ozone layer, and that attenuated or reduced the ozone level. And so the chlorofluorocarbons that we were using to spray our underarms and stuff was eating the ozone layer, and they had this big agreement between all countries of the Earth, the Montreal Accords, and we reduced using these ozone-eating chemicals, the chlorofluorocarbons. And that just shows that the nations of the Earth can agree and can accomplish environmental goals. And so the ozone levels are beginning to recover, and so that's a success story. Okay, we can do it. Place to start is methane. Okay, Janice says, what are the major sources of methane to the atmosphere? The main source, the anthropogenic sources, human sources, are natural gas and oil mining, coal mining, rice production. Rice grows in a wetland where there's flooded soil, so rice production, and also cattle production. Okay, so those are the human sources. And all of those are very controllable if we have the will to do it. And I want to say one thing I didn't say, like if we go back to, if I can go back to this, people always ask me, so here we have, here's the this record, and the temperature came up at the Holocene. We formed this interglacial here, and say, why don't we just going to go back into another glacial period? Like why, the orbital variations, why don't we just go back into another glacial period? And the reason for that is because CO2 now is just off the charts. It really is actually off this chart. There's CO2, there's methane. This whole period was called the Pleistocene, and the Holocene was just one little part of the Pleistocene. And if it wasn't for human influence, we probably would have gone back into another glacial period. But because now the greenhouse gases are off the charts, and the glaciers are melting, we have gone into a new period of time that's called, we're going to call it the Anthropocene. The Pleistocene is over. We're in a new geological epoch, the Anthropocene. And humans are a geological force, just like India ramming into Asia, just like plate tectonics. We're on par with these geological forces. And so the Pleistocene is over. We cannot rely on another glacial period to get us out of this mess that we're in. Okay, we have to solve this problem ourselves. As CO2 increases, Dennis Howard, does it affect the acidity of seawater and the ability of foraminifera to sequester carbonate? Absolutely, it does. CO2 goes from 280 to 420 over 200 years. CO2 is what we call carbonic acid. When CO2 dissolves in water, it forms an acid. Coca-Cola, those little bubbles in Coke, are carbon dioxide. The pH of Coca-Cola is 4. Okay, so ocean acidification is caused by increased CO2. And on millions of year timescales, the foraminifera, the corals, they can adapt to that. Okay, they can adapt to those changes. But on a 200-year time scale, that's just too fast. And so one of the problems is this ocean acidification. What's going to happen to the coral reefs? What's going to happen to oysters? What's going to happen to all of these things that are bivalves that have these shells? You know, that's another concern. What temperature for human habitation is considered problematic? I would say we are there now in some of in the Middle East, you know, that it gets so hot during the day that it's just, we're right at the edge of human habitation, I think, in some parts of the earth. And in India, you know, it's gotten hotter and hotter. Everybody wants an air conditioner. Those air conditioners still have these freon-like compounds that are really bad greenhouse gases. And of course, air conditioners leak. And so I think we're on the edge of that now. And then you see these mass migrations from Syria, like everybody wants to get out of Syria. And what are the problems there? Well, they're political problems, but they're also environmental problems as well.
Jeff, we're right up against 8 o'clock, friends.
Okay.
So we could do another one if somebody's got a real burning question.
Let me ask you, was my presentation clear? Did y'all get the time scale thing here? You know, the million year, 100,000 year, 1,000 years. Yeah, good.
Seeing lots of thumbs up. Well, thank you so much for your time, Jeff,
Sure.
and coming to share with us tonight. We appreciate it greatly.
Anybody like to email me, jchanton, JCHANTON at fsu.edu, and I can furnish you references and further reading.
Okay, thank you.
Thank you.
Sure. Thank you. Thank you for listening. Thank you for your attention.